Hello everyone and welcome back to our Docker series on TechOps Tutorial. In the previous video, we learned what Docker is, how Docker images and container work, and how to create and manage containers. Now it's time to learn one of the most important topics in Docker, that is Docker files. Docker files allow us to create our own Docker images instead of always using the images that someone else has already built. This is an essential skill for system administrator, DevOps engineer, and developer because in real world project, you will often need to package your own application into a Docker image. In this video, we will start from the basic. We will understand what Dockerfile is, explore the most commonly used Dockerfile instructions, learn how Docker builds the image, see how layer caching speed up the build process, discuss Dockerfile's best practice, get introduced to multi-stage build, and finally, compare Dockerfiles with Docker Compose. So let's get started by understanding why Docker files are needed in the first place. Now that we know what we will cover in this video, let's first understand why Docker files are needed. Imagine you have developed a Python application and want to run it inside a Docker container. Without a Docker file, every time you create an image, you will have to repeat the same setup steps manually. You will need to install Python, install all required packages, copy your application files, set any environment variables, and finally start the application. Now imagine you are working with multiple server or a different team members. Repeating these steps again and again is time consuming, and there is always a chance that someone might miss a step or configure something differently. This is where a Docker file helps. A Docker file allows us to describe the entire application setup in a simple text file. Once the Docker file is ready, Docker can automatically build the image by following those instructions. As a result, every image is built the same way, whether it's on a laptop, another developer machines, a test server, or a production server. The biggest advantage is consistency and repeatability. Instead of manually performing the setup every time, you simply run the docker build command and the Docker take care of rest. Now that we understand why Docker files are needed, let's answer the next question. What exactly is a Docker file? A Docker file is a text file that contains a list of instructions. Docker reads these instructions one by one to build a Docker image. You can think of it as a recipe. Just like a recipe tells you how to prepare a dish step by step, a Docker file tells Docker how to build an image step by step. A Docker file is usually saved with a file name Dockerfile without any file extension, and the instructions are executed from top to bottom in the order they are written. Once the Docker file is ready, we use the docker build command to create a Docker image. That image can be used to start one or more container using docker run command. So the overall workflow is simple. We write a Docker file, Docker builds an image from it, and then we create a container from that image. The important point to remember is that Docker files creates the images and images creates a container. Now that we know what a Docker file is, let's look at its basic structure. On the left, you can see a simple Docker file for a Python application. Don't worry, if some of these instructions looks new, we will learn each one in detail over the next few slides. Let's quickly understand what is Dockerfile is doing. First, we start with a Python base image using the from instruction. Next, we set working directory inside the container to /app. After that, we copy the requirement.txt file into the image and install all required Python packages. Once the dependencies are installed, we copy the rest of the application files. Finally, the cmd instruction tells Docker which command to run when a container starts from this image. There are three important things to remember about every Docker file. First, each instruction is written on a separate line, making the files easy to read and maintain. Second, Docker executes the instruction from top to bottom, so the order of the instruction is important. Third, the most Dockerfile instruction creates image layers, which helps Docker reuse the unchanged part of the build. and makes further build faster. We will understand image layers and caching in more details later in this video. Now that we have seen the basic structure of a Dockerfile, let's get familiar with the most commonly used Dockerfile instruction. Think of these instructions are building blocks. Each one has a specific purpose and together they tell Docker exactly how to create an image. Let's briefly look at each one. The from instruction specifies the base image that our image will be built on. The run instruction executes command while the image is being built. For example, it's commonly used to install software or require packages. The copy instruction copies files or folders from your local machine to a Docker image. The cmd instruction defines the default command that runs when the container starts. The entry point instruction also control what runs when the container starts, but it is mainly used when you want container to always run a specific program. The expose instruction document which network port the application uses inside the container. The env instruction is used to define the environment variables that the application can use while running. And finally, the work directory instruction sets the working directory for the instruction that follows. Don't worry about remembering all of them right now. In the next few slides, we will look at the most important instruction with simple example. The important thing to remember is that every Dockerfile instruction has a specific job during the image creation process. Let's start with the first and one of the most important Dockerfile instruction from. The from instruction tells Docker which base image to use for building your own image. You can think of it as the starting point of your Docker image. For example, if you are developing a Python application, you can start with the official Python image. If you are building a Node.js application, you can use the official Node.js image. Or if you want a minimal Linux environment, you can start with Ubuntu image. That's why you can see example like from Ubuntu colon 24.04, from Python colon 3.12, from Node colon 20 hyphen Alpine. But why do we need a base image? The reason is simple. Your application does not run by itself. It needs an operating system, the required runtime, and sometimes additional tools or libraries. Instead of creating everything from scratch, Docker let us build on top of existing image that already contains what we need. As shown in the diagram, your application sits on the top of selected base image. That base image may already include a Linux operating system and a runtime like Python. All of this still shares the host machine Linux kernel. In most cases, from is the very first instruction in a Docker file because Docker needs to know the base image before it processes the remaining instructions. Now that we know how to choose a base image using the from instruction, let's look at three more Dockerfile instruction that you will use in almost every Dockerfile. Let's start with run. The run instruction is used to execute command while the Docker image is being built. It's commonly used to install software, download files, or prepare the application environment. For example, you might update the package list, install Python packages, or install additional tools like curl. Next is copy. As the name suggests, the copy instruction copies files or folders from your local machine into a Docker image. For example, you can copy your application source code, configure the files, or the requirement.txt file that contains your project's dependency. And finally, we have WORKDIR. The WORKDIR instruction sets the working directory inside the image. Once it's set, the instruction that follows, such as run, copy, and cmd, use this directory by default. For example, if your working directory is set to /app, any files you copy using a relative path will be placed inside /app. And commands like pip installed or python app.py will also run from that location unless you specify another path. These three instructions works together to prepare your application before it runs. So far we have learned how to prepare our application while building the image. Now let's understand what happens when the container actually starts. This is where the CMD and entry point instruction comes into play. Let's begin with CMD. The CMD instruction specifies the default command that Docker runs when a container starts. For example, if your Docker command contains cmd python app.py, Docker will start the application by running that command when the container is created. One more important thing to remember is that cmd can be overridden when you run the container. If you provide another command with docker run, Docker uses that command instead of one defined in cmd. Now let's look at an entry point. The entry point instruction also defines what runs when the container starts, but its purpose is little different. Instead of providing a default command, it defines the main executable for the container. Any additional argument you pass with docker run are added to that executable. That means entry point is generally harder to override than cmd, making it useful when you always want the container to run a specific program. A simple way to remember the difference is cmd provides the default command that can be changed. Entry point defines the main program that the container is designed to run. Both instructions control how the container starts, and in many real-world Docker files, you will often see them used together depending on the application requirements. Next, let's look at two more useful Dockerfile instructions, expose and env. We will start with expose. The expose instruction is used to document the network port that your application listens on inside the container. For example, if your application listens on the port 5000, you can write expose 5000 in the Docker file. You can also specify the protocols such as expose 8080/TCP, although the TCP is the default in most cases. One important thing to remember is that expose does not publish the port to your host machine. It simply tells anyone using the image which port the application is expected to use. To make the application accessible from outside the container, you will still need to map the port when running the container using -p option with docker run command. Now let's look at the env instruction. The env instruction is used to define the environment variables. These variables can be used by your application or by other instruction that comes later in the Docker file. For example, you might set the application environment to production or define the port that your application should use. Using environment variable makes your Docker file easier to manage because you don't have to hardcode configuration values throughout your application. So while expose document how your application communicates over the network, env helps configure how your application behaves. Next. Now let's understand an important concept behind the Docker image build, that is image layers. When Docker processes a Docker file, it does not create one big file all at once. Instead, it builds the image step by step, and most instruction creates a new layer on top of the previous one. Let's look at the example on the left. We start from Python 3.12, which creates the base layer. Then WORKDIR/app adds the information about the working directories. Next, copy requirements.txt creates another layer. After that, run pip install -r requirements.txt creates a new layer containing the installed packages. And finally, copy adds the application files as the top layer. On the right side, you can see how these layers are stacked together to form the final Docker image. Why is this important? Because Docker can reuse the layers that haven't changed. If your requirement.txt file stays the same, Docker may reuse the layer that contains the installed packages instead of installing everything again. This is one of the reasons Docker builds can be much faster after the first build. The key point to remember is that most Dockerfile instructions create image layers, and Docker combines those layers to create the final image. Now that we understand Docker image layers, let's see why they are so useful. One of the biggest advantage of layer is Docker layer caching. Let's look at the two example on the screen. On the left is the first build. Since the Docker has never built this image before, it has to execute every instructions in the Docker file. It starts with a base image, sets the working directory, copies the requirement.txt file, install the required packages, and finally copies the application files. As a result, every layer is built from scratch. Now look at the second build. Let's assume we only changed our application code and did not modify requirement.txt file or any of the early instructions. Docker checks each layer one by one. If a layer has not changed, Docker simply reuses it from the cache instead of building it again. That's why the layers from the base image, working directory, copied requirement.txt, and installed packages are marked as cache. Only the last layer, which copies the application file, needs to be rebuilt because that's where the changes occurred. This is why the Docker build becomes much faster after the first build. That's also why the order of instruction in a Docker file is important. Instruction that changes less often, such as installing dependencies, should usually come before the instructions that copy the frequently changes application code. This allows Docker to reuse more cached layers and reduce the build time. The key takeaway is simple. Docker reuses the unchanged layer whenever possible, making image build much faster. Now that we have learned how Docker builds images and use layer caching, let's look at some best practice for writing a better Docker files. This practice will help you build images that are easier to manage and faster to build. The first recommendation is to use the official images whenever possible. Official images are maintained by trusted source and are a good starting point for most applications. For example, you can use the official Python, Ubuntu, or Node.js images from the Docker Hub. Next, keep your images as small as possible. Smaller images takes less time to download, upload, and deploy. They also use less storage space. Another important practice is to use .docker ignore file. Just like a .git ignore file tells Git which files to ignore, a .docker ignore file tells Docker which files and folders should not be included in the build context. For example, you can exclude log files, temporary files, or folders like node underscore modules that don't need to be copied into the image. It's also good idea to minimize unnecessary layers. For example, if you have a multiple related commands, you can often combine them into a single run instruction. This helps keeps the image simpler. Next, remember that the order of instruction matters. Instructions that rarely change, such as installing dependency, should usually come before copying the application code. This allows Docker to reuse cached layers and speed up future builds. Finally, never store secret in your Docker file. Avoid hard-coding APIs key, passwords, or access tokens into an image. Instead, provide these information securely at a runtime using an environment variables or a secret management solution. Following these best practice will help you create a Docker images that are secure, smaller, and faster to build. So far, we have learned how to write Docker files and how to build Docker images efficiently. Now let's briefly introduce another useful concept called multi-stage build. Don't worry, we will cover this in detail in a dedicated video later. For now, let's understand the basic idea. On the left is a traditional build. In this approach, everything is included in the final image. That means your source code, build tools, compilers, and application dependency all become part of this image. As a result, the final image becomes larger than necessary. Now look at the right side. With a multi-stage build, the process is divided into multi-stage. In the first stage, Docker uses a builder image to compile the application or prepare everything that's needed. Once the build is completed, Docker copies only the required application files or binaries into a second. much smaller runtime image. The build tools, compilers, and other temporary files are left behind in the first stage and are not included in the final image. The result is much smaller production image that is easier to distribute and deploy. So the main idea is simple. Use one stage to build the application and another stage to run it. We will keep things simple for now and explore multi-stage Docker files with practical examples in a separate video. One question that beginner asks all the time is, if I have a Docker compose, do I still need a Docker file? The answer is yes, because they solve the different problem. Let's start with the Docker file. A Docker file is used to build an image. It defines what goes inside the image, such as the base operating system, installed packages, application files, environment variables, and the startup command. When we run a command like docker build-t my app followed by dot, Docker reads the Docker file and creates an image. Now let's look at a Docker compose. Docker compose is used to run and manage multiple containers together. For example, a web application may need a front-end container, a back-end API container, a database container, a cache container. Instead of starting each container manually, Docker Compose allows us to define all of them in a single file and start them together using Docker Compose up. A simple way to remember the difference is Dockerfile defines how to build one image. Docker Compose defines how multiple containers work together. In real projects, they are often used together. Dockerfile builds the application image and Docker Compose starts that image along with any supporting services. So these tools are not competitors. They complement each other and solves different part of the container workflow. So far we have learned the theory behind Docker files. Now it's time to put everything into a practical. In this hands-on demo, we will build a complete Docker image from scratch using simple Python application. Next, we will see Docker layer caching in action by making a small code change and observing how Docker intelligently reuse unchanged layer to speed up the build process. Finally, we will compare a poorly optimized Docker file with an optimized one to understand why the order of instruction matters, how Docker cache works, and how a few small changes can significantly improve the build performance. By the end of this demo, you will not only know how to write a Docker file, but also how to write one that builds faster and follow the real world best practice. Let's switch over to our terminal and get started. Before writing our Docker file, let's first verify that Docker is installed and running correctly. You can verify with the command docker -version or docker info. You can also check the images. There is no any image. Docker ps. There is no any running container. Docker version confirms the Docker is installed. Docker info shows the Docker engine is running. Docker image displays locally available image. Docker ps shows the currently running containers. Now let's create a new project directory. This will contain our application and Docker files. Dockerfile-demo. You can check pwd. The directory is empty. Now that our project directory is ready, let's create our first application file. We will keep the application very simple because today's goal is to learn the Docker files, not Python programming. Let's create a simple Flask application. am.py. I will just copy paste the Python code. This is the code. Save the file. Our application simply returns hello from Docker whenever someone accesses the home page. Our application uses Flask. So Docker needs to know which Python packages to install. For that we will create requirements.txt, flags, save the file, requirements.txt. This file lists all Python dependencies required by our application. Now we will create our first Docker file. Instead of explaining the entire file at once, let's understand each instruction as we write it. Docker file. Here I will write from Python colon 3.12. This tells Docker to start from the official Python 3.12 image. Next is working directory, WORKDIR/app. This sets the default working directory inside the container. Next is copy requirements.txt. We first copy only the requirement file and then run pip install -r requirements.txt. Docker install the required Python packages during the image creation. Copy. Now Docker copies the remaining application files. Then we will expose the port. I'm using 5000. This documents that our application listen on port 5000. cmd python app.py. This is the command Docker execute when container starts. Save the file and verify it. From Python working directory, copy, run, expose cmd. Okay. Now let's verify the project files. ls-l app.py, docker files, requirements.txt. Our project is now ready. We have the application code, the dependency file, and the Docker file. The next step is to ask Docker to build an image from these files. Now Docker will execute these instructions one by one and create an image. Let's understand the build command before running it. Docker build -t /-demo :v1. This is the command. Docker build starts the image build. -t assign an image name and tags. In our case, the image name is Flask-demo and the tag is v1. The dot at the end tells Docker to use the current directory as the build context. Docker will look for the Docker file and any required files in this directory. Now let's run it. Failed to build, failed to solve, Docker file phrase error, copy requirement list, 2 arguments. My bad. Docker file, it required 2 arguments. You need to mention dot. Let's rerun. Here you can see load the first line. The Docker file loaded. Load build definition from Docker file. Docker first reads the Docker file to understand the instruction it needs to execute. Base image downloaded. Here you can see load metadata for docker.io library /python 3.12. Since this is the first time I am using Python 3.12 image on this machine, Docker downloads it from the Docker Hub. In future builds, Docker will reuse this image locally, so this download won't happen again unless the image is removed or updated. I will pause the video and resume back once this is done. Here you can see 2x5 working directory /app copies the requirement, run the pip install command, and then copy. Now Docker execute each instruction from the Dockerfile in order. It creates the working directory, copies the dependency files, install Flasks, and finally copies the application source code. And then you can see exporting to image. Once all the instructions are completed, Docker packages everything into a new image. The most important line is naming to a docker.io/library/flask-demo:\v1. This confirms that our image has been created successfully with the name flask-demo and the tag is v1. Now let's verify the image. You can verify with Docker images. The build completed successfully and we can now see our custom image name flask-demo with the version 1 tag. If you are already having a multiple images, you can directly filter it with Docker image ls flask-demo. If your system contains many images, you can filter the list by repository name to quickly find the image you are looking for. You can also inspect the image by using Docker image inspect flask-demo:\v1. This command displays the detailed information about the image. You don't need to understand every field right now. Just remember the Docker stores a metadata about every image it creates, and the Docker image inspect lets you view that information whenever needed. Our image is ready. The next step is to create and start container from this image. Docker run -d name +-demo, provide the port 5000 demo:\v1. Let's quickly understand this command. Docker run creates and start a new container from the image. -d option runs the container in detached mode, which means it runs in the background. -name option assign a meaningful name to a container, making it easier to manage later. -p 5000:5000 maps port 5000 on the host machine to a port 5000 inside the container, allowing us to access the application from outside the container. As you can see, the output, Docker returns the container ID, which confirms that the container has been created successful. Now let's verify. Docker ps. The Docker ps command shows all currently running containers. You can see the container name. This is the container name flask-demo. The status is up and the port mapping is here. This confirms that our container is running and listening on port 5000. You can run docker port flask-demo. This command shows the port mapping configured for the container. Here we can confirm that the port 5000 inside the container is mapped to the port 5000 on the host. Now let's verify the application. You can run curl http localhost 5000. Here you can see you receive the output hello from Docker. Curl sends the request to our application. If everything is working correctly, we should receive the response returned to our Flask application. Expected output is hello from Docker. Perfect. This confirms that our application is running successfully inside the container. Now let's verify the application on a browser. Now type http://5000. You can see hello from Docker. Minimize it. We have successfully created our own Docker image using Dockerfile, started a container from that image, and verified that application is working from both the terminal and the web browser. Now let's see the demo 2 Docker layer caching. Our application is already running successfully. Now let's explore one of the Docker biggest advantage, Docker layer caching. Instead of rebuilding the entire images every time, Docker reuses the layers that haven't changed. This helps reduce the build time, especially for large applications. To demonstrate this, I will make a small change to the application app.py. I will change return hello from Docker to return hello Docker. We'll write something like layer layer cache. Save the file. I will show you what I have changed. I have changed only hello from Docker to hello Docker layer cache. We only change the application code. The Docker file and the dependency file remains exactly the same. Let's rebuild the image and observe what Docker does. I will rebuild the image using a new tag so we can easily distinguish it from the previous version. Docker build. We are in the same directory. Build -t demo v2 space dot. Here you can see cache working directory, cache copy, cache run pip till here. This time the build completed much faster because Docker reused the layer that did not change. As you can see this line, working directory, the WORKDIR instruction has not changed, so Docker reused this layer. The next instruction is copy requirement.txt. This file is unchanged, so Docker reused this layer as well. And the next is run pip install -r requirement.txt. Since the dependency file did not change, Docker did not install Flask again. Instead, it reused the previous build layer. And the last one is copy. Only this step was executed again because we modified app.py, and this instruction copies our application files into the image. This is exactly how Docker layer caching improves build performance. Instead of rebuilding every layer, Docker reuses unchanged layers and rebuild only the layer affected by your changes. Now let's see another demo. Demo 3, Dockerfile optimization. Why instruction order matters. In the previous demo, we saw Docker reuse cache layer to speed up the build process, but Docker layer cache works best only when the Docker file is written correctly. Let's see how the order of Dockerfile instruction can affect the build performance. Let's first look at our current Docker file. This is our current Docker file. Notice that first we only copy the requirement.txt file, install the dependency and then copy the application code. This is considered a good practice because application code changes more often than the dependency files. Now let's intentionally write a poorly optimized Docker files. I will edit the same Docker file. Here we'll keep from work directory. Just I will remove this line. Instead of this, I will write dot space dot and we will remove this line. Let's save the file. See the difference? Just I have removed this line and shifted this instruction above. Notice the difference. This time we are copying the entire project before installing the Python packages. Since copy instruction copies every project files, even a small change to app.py changes this layer. As a result, Docker cannot reuse the next layer and has to run pip install again, even though the requirement.txt has not changed. Let's build the image and see this behavior in action. Now let's build the image using poorly optimized Dockerfile. Docker build -t -demo colon. I will give version as bad dot. Here you can see working directory is cached. Docker reuse the working directory layer because this instruction has not changed. The next instruction copy. Docker copies the entire project into the image. Since this layer is different from our previous Docker file, Docker had to build it again. And the next is run pip install. Notice that Docker also executed the run pip install instruction even though the requirement.txt file has not changed. Docker could not reuse this layer because the previous copy instruction layer changed. This is exactly why copy before installing the dependency is considered a poor practice. Now let's make a small change to our application and rebuild the image once more. You will see Docker repeats the dependency installation again even though the dependency file has not changed. Let's modify the application. Here what I will do, I will change hello docker layer cache to hello docker optimization. Save the file. This is the file. Just I have changed this line, hello docker layer cache to hello docker optimization. Now I have made a small change to our application. Let's rebuild the image and see what Docker does. Docker build -t -demo colon bad -v2. Sorry. Here you can see cache 2x4 working directory app. Docker reused the working directory layer because nothing related to it changed. Then the next is copy. Since we modified app.py, Docker had to execute copy instruction again because it copies the entire project. Then run pip install. Notice that the Docker also executed run pip install instruction again. But we did not change requirement.txt, we only changed app.py. Because the previous copy layer changed, Docker could not reuse the dependency installation layer. As a result, Flask was installed again even though nothing changed in the dependency file. This is unnecessary work and increase the build time. That's why copying the entire project before installing a dependency is not recommended. Now let's restore the optimized Docker file and compare the difference. You will see that after a small code change, Docker reuses the dependency layer instead of installing everything again. Now let's restore our optimized Docker file. This time we will copy the dependency file first, install the required packages and only then copy the application code. I will edit the Docker file. Here what we will do, we will add the instruction requirements.txt and here we will add copy, save it. This is the Docker file. Now let's build the image again using the optimized Docker file. I will run the same command, docker build -t flask -demo. Now I will change the tag to optimized. So you can see the difference. Now again I will modify the application. Here what I will do, hello docker optimization to hello docker optimized build. We can do optimized. This look good. Okay. Save the file. See the difference? Only this line I have changed. Earlier it was hello docker optimization. Now I just modified a line with hello docker optimized build. Now let's again build with a customized -v2. You can see the Docker reused this layer because the dependency file did not change, and the run pip installed -r requirement.txt. This time the Docker skipped installing Flask because it reused the cache layer, and also the copy. Only the application layer was rebuilt as we modified to optimize build. Let's compare both Docker files. In the poorly optimized Docker file, changing just app.py caused Docker to install the dependency again. In the optimized Docker file, Docker reused the dependency layer and rebuilt only the application layer. This is why the order of instruction in a Docker file is so important. A well-structured Docker file helps Docker reuse the cache layer, resulting in faster build and avoiding unnecessary work. Our demo is completed. Let's clean up the container. Docker ps, docker stop. It's not mandatory, just I want to show you the command how to clean up. Docker ps, docker ps -a, docker rm -demo. It is also gone. We can check Docker images. These many images we have created. The container has been removed. While the images is still available locally, we can create a new container from this image anytime without rebuilding it. So that's everything we covered in this Dockerfile session. We started by understanding why Dockerfiles are important and how they help us create the same image every time. Then we learned the complete image build process and the basic structure of Dockerfile. After that, we looked at the most common Dockerfile instructions like from, copy, run, working directory, cmd, entry point, expose, and env, and saw what each one does. We also learned how Docker use layers, why layer caching makes build faster, and how to write Docker files in a better way. Finally, we covered multi-stage build, fixing build errors, and preparing images for production. At this point, you should be comfortable writing your own Docker files and building Docker images with confidence. Thanks for watching, and I will see you in the next one.